Welcome to our free lecture, sponsored by the Nick and Maggie D. Wolf Foundation. The Nick and Maggie D. Wolf Foundation has supported lectures for since 1985, which is 40 years. So their generosity and the generosity of our lecturers make it possible for us to share our science with the public, which we are very, very happy to do. This is our way of giving back and thanking the Aspen community for supporting the center these very many years. We really appreciate it. So just to say a little bit about the center and about our conference. So during the winter, we have groups of physicists who come here, up to 110 physicists at a time. We spend a very intensive week sharing the latest research with each other, making presentations, and then also having informal and formal meetings here, but also on the lifts, out snowshoeing, etc. It gives us a chance to talk about our vision, to discuss recent results. And this week's conference is called "Empowering the New Vision in High Energy Physics." This week we were discussing recent results in particle physics, neutrino physics, etc. And in addition to that, we were thinking about, how to maximize the use of current large-scale particle physics experiments like Georgia will be talking about today. And then also thinking about empowering the future. So thinking about what we can do in the next 10, 20, 30 years, where we should put our resources, and how we can continue to unlock the mysteries of the universe. So it's been quite a lot of fun. And I don't know, I have a feeling that all of you enjoyed the mountains. It's been really refreshing just getting out, having the opportunity to think deeply and seeing these beautiful landscapes and thinking big about what we want to do over the next couple of decades. So without further ado, it is my great pleasure to introduce tonight's distinguished speaker, a scientist at the forefront of some of the most fascinating frontiers in modern physics. So Professor Karagiorgi is a leading researcher in experimental particle physics from Columbia University and dedicated to solving the mysteries of the universe through the study of neutrinos, which you'll talk about tonight. Neutrinos are some of the most elusive and enigmatic particles known to science. And I have a huge amount of respect for Georgia. She's a great friend of mine, so I think you'll really enjoy this lecture. As a faculty member at Columbia University, her work has focused on studies of neutrinos, high-energy gamma rays, and searches for dark matter. She is deeply involved in groundbreaking international collaborations, such as Dune. Dune is the deep underground neutrino experiment, which you'll hear about more today. And also in Microboon. These ambitious projects aim to answer fundamental questions about the universe in terms of things like neutrinos, matter, antimatter, and even, understanding more about the very fabric of the cosmos. Beyond her research, Professor Karagiorgi is also a passionate advocate for STEM education and public engagement, which is why we're so excited to have her here with you tonight. And she really enjoys making the complexities of particle physics accessible to a wider audience. So, without further ado, please join me in welcoming Professor Karagiorgi. Thank you so much.
Thank you very much, Isabel, for the kind introduction. Thank you to the Nick and Maggie de Wolf Foundation for their support, and thank you to all of you. Thank you to all of you for coming here today. I'm very excited to tell you a little bit, actually, about what I do and why I do it, and why I find what I do exciting, compelling, inspiring. So join me as we take a look into our sky. If we look into our sky, what we see is stars, planets, galaxies, neutron stars, white dwarfs, stuff made of matter, predominantly neutrons, protons, and electrons. We know that that's not the only thing that's out there. We know there's stuff that we cannot see. About 5% of the stuff making up our universe is dark matter. And we know it's there because we can see its gravitational effect and other visible matter. We also know that there's some other stuff that makes up 70% of our universe, roughly, that we more or less have no idea what it is, and we call dark energy. It is there, is responsible for the accelerated expansion of our universe. Okay, so all of this is what came about of a hot soup that was created after the Big Bang. So in this massive explosion, of space, time, energy, and matter of the universe was created. And this giant explosion hurt matter everywhere. And it's also what caused the accelerated expansion of our universe. As our universe expanded, it cooled down and everything settled into the stuff that we see around us today. Okay, the 5% dark matter, 20% ordinary matter, 25% dark matter, and 70% dark energy. So we don't know exactly what dark matter is. We have no idea what dark energy is. That's not the only weird thing about our universe. What's also very confusing is, and particularly strange, is that what was left over after the Big Bang is an excess of matter over antimatter. So that is a very profound question in particle physics and cosmology. This is one of the biggest mysteries that we're trying to solve today. And it's of fundamental importance. According to theory, we know, and according to all the laws of physics that we confirmed so far, know that during the Big Bang, equal amounts of matter and antimatter should have been created. Yet, they exist here today, made of matter. When we look out in the sky, we see stars, we see galaxies. We don't see anti-stars, we don't see anti-galaxies, we don't see anti-Earth. So how did that come about? This is the mystery that we're trying to solve. But first, what is antimatter anyway? Any Star Trek fans in the audience? Great. So you might be familiar with the Star Trek Starship Enterprise and their method for traveling at speeds greater than the speed of light, being matter, antimatter, annihilation, propulsion. So according to Star Trek, antimatter releases lots of energy when it meets matter. And this is the energy that propels a starship. In a sense, that is possible. It's not possible to travel faster than the speed of light. Such large energy can be released. And there are, in fact, people thinking about it. But we're not quite there yet. Some of you might also be familiar with antimatter in the film or the book Angels and Demons, where Professor Langdon tries to save the Vatican City from an antimatter bomb. This scenario is a little bit more far-fetched. It's actually extremely difficult to put together such large amounts of antimatter to make such a bomb. But antimatter is not just science fiction. It's real, and it's out there, and we can detect it, and we can and have measured it. For example, small amounts of antimatter rain down upon us constantly on the Earth from cosmic rays, which are very energetic particles from outer space. These antimatter particles reach our atmosphere at a rate that can range from 1 to 100 per square meter, depending on its type. We can also produce antimatter at accelerators around the globe, very much angels and demons style. Antimatter is also produced in nuclear decays. This could be decay of radioactive elements around us, or in nuclear reactors, for example. But there are also other sources of antimatter which are much closer to home. For example, bananas. Banana will emit an antimatter particle every little bit more than an hour or so. That's because bananas contain traces of potassium isotopes that are radioactive. These decay, producing among their byproducts also antimatter particles. Um, and if you like me and you like bananas or kiwis for that matter, then your body also produces antimatter in the amount of time that it takes to digest a banana. Okay, so let's zoom in a little bit. So, okay, universe is made, or at least the stuff that we can see in our universe is made primarily matter. And actually, protons and neutrons are made of fundamental particles that we call quarks. They're up and down type quarks that make up protons and neutrons. And so most of the visible universe around us is made up of up and down quarks and electrons. These are not the only fundamental constituents of matter. We know that there are heavier versions of these. There are heavier versions of the up and down quark, which are the charm and spinach quark, or even the heavier top and bottom quark. There are heavier versions of electrons, which we call muons and taus. And there are also lighter versions and electrically neutral versions of the electron, which we call neutrinos. And this is the stuff that primarily makes up our visible universe. Fundamentally, all these particles are excitations of a quantum field that permeates everywhere. And these excitations pop out of this space-time extending field, much like bubbles in boiling water. And for every particle, there's also an equal and opposite antiparticle, which represents an opposite excitation of this field, and which has the exact same properties and mass, but opposite charge. And since particles and antiparticles have opposite charge, then when a particle and antiparticle come together, they completely annihilate each other, leaving behind just energy. So every particle has its own antiparticle. An electron's antiparticle is a positron. A neutrino's antiparticle is an antineutrino. A muon's antiparticle is an antimuon. They all obey the same laws of physics. They obey the same laws of electromagnetism. The same laws govern their decays or their interactions. And since they obey the same laws, then the antimatter, just in the same way that matter does, can come together, and antiquarks can bind into antiprotons or antineutrons. Those can bind together into antinuclei. They can bind together with positrons and make antiatoms. And in principle, of antimatter could have formed a whole other universe that's made of anti-Earth, anti-stars, anti-galaxies. But that's not the case, okay? And it's a big question to ask, where is all the antimatter? Everything that we see around us today came about, we think, after equal amounts of matter and antimatter produced during the Big Bang annihilated early on in the cosmological age of our universe, with the exception of something like 1 in a billion matter-antimatter particle pairs. So everything we see around us, everything that is making up our observable universe, that's the result of a small, tiny asymmetry in the amount of matter over antimatter prevailing. Okay? So As far as we know, um, in order for this to come about, some form of asymmetry from new physics must have been responsible early on during the cosmological history of our universe, which somehow tipped the scales enough such that matter in the end prevailed. And we don't know for sure what that something is, but we think that it might have something to do with neutrinos. Okay, so neutrinos are, as the name suggests, little neutral particles. They're kind of like the electron, but much, much lighter and electrically neutral. They are fundamental particles of matter, and they come in three types: the electron neutrino, mu neutrino, and tau neutrino. And there's lots of sources of neutrinos out there. The Big Bang, neutrinos from the Big Bang, in fact, are so abundant, they actually played a role in the evolution of large scale structure in our universe and how galaxies and stars formed and came to be over time. And we can, in fact, measure the effects of Big Bang neutrinos, these cosmic neutrinos, on large scale structure. Supernova explosions are the biggest, most abundant sources of neutrinos out there. This is an image from Supernova 1987A, which was one of the biggest stellar explosions that was recorded since the invention of the telescope 400 years ago. This is a Hubble telescope image taken actually 3 years after the supernova took place. And we have been able to actually measure neutrinos from this supernova in a big underground detector. We've been able to even constrain some of the neutrino properties by measuring them. There are also other astrophysical sources of neutrinos. I don't know if any of you happen to run into this article in the New York Times a couple of weeks ago. We think that what was recently reported as the highest energy particle to be ever observed and measured might have come from some astrophysical source. Our sun or any star in our cosmic universe also emits a lot of neutrinos. Stars produce neutrinos because they're fueled by nuclear reactions, which produce neutrinos. Our sun is a giant nuclear reactor. This is actually the sun, an image of the sun observed in neutrinos. The detector that's actually looking at the sun at night, right through the Earth. So it's recording neutrinos from the sun coming through the Earth and some fraction of them interacting in the detector. And this is the image that they're able to reproduce. As a giant nuclear reactor, our sun is actually the second most abundant steady source of neutrinos for us here on Earth. About 65 billion neutrinos pass through your fingernail, from the sun, through your fingernail every second. And another interesting fact about neutrinos is that unlike photons, which can take hundreds of thousands of years to travel from the center of the sun to the edge of the sun, neutrinos can stream through the sun just like that in the matter of seconds. So if for some reason someone were to go inside our sun and flip its fusion switch off, wouldn't know by looking at light from the sun. But if we're able to see the sun in neutrinos, we would know within minutes. Nuclear reactors also produce neutrinos through fission processes. And we've actually been able to detect reactor, actually antineutrinos, decades. Our Earth contains heavy radioactive elements in its mantle and crust. We've actually been able to measure the geoneutrino flux due to these elements and been able to produce these heat maps that tell us how neutrinos from radioactivity in the Earth looks like on the Earth's surface. Of course, bananas. As I mentioned earlier, potassium, traces of a radioactive isotope of potassium can be contained. It's actually abundant in nature at the level of 0.01%, naturally abundant. There's actually something called a banana equivalent dose. It's about 1% of your daily radiation dose. To help give you a sense of scale, so nuclear reactor power plants have maximum radiation leakage restraints, which are equivalent to 2,500 banana equivalent doses per year. A chest CT scan is about 70,000 bananas, and a lethal dose of bananas corresponds to 35 million bananas. That is actually keep potassium levels constant through a process called homeostasis. I don't think it's because of radioactivity. I think there's other reasons having to do with how your heart pumps. But basically, you would need to eat 35 million bananas in a very short amount of time to receive a lethal dose, or at least within the amount of time that it takes to digest the banana. So it's not really something that we have to worry about. And of course, once we eat even 1 or 2 bananas, then we are emitters of neutrinos ourselves. Okay, so lots of sources. And in fact, neutrinos are everywhere. They're the second most abundant known particle in the universe after photons. And they're the most abundant matter particle in our universe. From the sun alone, with every second that goes by, something like 1,000 trillion neutrinos will go through your body without leaving a trace. 10 to the 29 neutrinos will go straight through the Earth, most of them without leaving a trace. And one such neutrino from the sun would actually have a good chance of going through 200 Earths for having a reasonable chance of interacting. So all that means is that neutrinos are very feebly interacting. Okay. And the reason that is the case is because they're electrically neutral. And so they're immune to the processes that normally block particles from going through matter, from traversing large amounts of matter. These processes are primarily electromagnetic in nature. So neutrinos barely interact with other particles. And actually, the only way they interact is more or less through a head-on collision with either a nucleus, an atom, or an electron in the electron shells. That doesn't happen very often. But we care to study them, and we have, in fact, been studying them for decades. And the recipe for doing that involves finding or building very intense neutrino sources. Also building very large, dense, and sensitive detectors that serve as interaction targets for these neutrinos. And of course, being patient and waiting for long enough that we can accumulate enough interactions and be able to study neutrinos and how they interact with matter and their properties with high enough precision. So the reason why neutrinos are so hard to catch is because they only interact through the so-called weak force. There are three types of forces that govern most particle interactions. The most prevalent one in our everyday lives is the electromagnetic force. Taking off your jacket on a very dry day and your hair sticking up due to static electricity, that's electromagnetic force. That's the same force that binds electrons to nuclei to form atoms. There's also another force, fundamental in nature, which is responsible for holding the nucleus together so that it doesn't come apart to Coulomb electromagnetic force repulsions between the protons. That's the nuclear force, and it's about 100 times stronger than the electromagnetic one. And comparatively to these two, the weak force, the force that governs neutrino interactions, is about 10 orders of magnitude smaller. Okay? So this is the reason why neutrinos are such a pain to work with. But these interactions do happen. All that it means is that they happen very rarely. This is an example of one such weak interaction involving neutrinos. It's actually a nuclear decay. It's a decay where a neutron, it could be free or in the presence of a nucleus, decays and breaks into a lighter proton and then gives off that remaining energy in the form of an electron and an electron antineutrino, in fact. This process on the left is how we can produce neutrinos, in this case, antineutrinos. But neutrinos and antineutrinos, like matter and antimatter, they're actually related under time reversal symmetry. So that same process we can rethink as a neutrino hitting neutron, producing an electron and a proton. And this is actually how we can detect neutrinos in our detectors. We detect an electron neutrino by looking for an electron and a proton to be produced in our detectors. Those particles are electrically charged, and so they will leave some signature, some visible signature behind. In a similar way, a muon neutrino interact, and rather than producing an electron, it will actually produce a muon as well as a proton. We can see that in our detectors as well. And similarly, a tau neutrino interacts to produce charge tau. And so by studying what is produced in neutrino interactions in our detectors, we can actually infer not just that there was a neutrino interaction, but additionally that a neutrino of a certain type was the one that interacted, an electron neutrino or muon neutrino or tau neutrino. How do we see particles in our detectors? How do we see these muons and electrons and protons? So we rely on the effects of electrons, muons, protons that they cause when they encounter matter in their path. So these particles, when they're energetic enough, what they do is that they excite the atoms along their path. Okay? For example, they can ionize the atoms and release ionization electrons along their path. We are able to build detectors that can measure those ionization traces. This is an example of such a detector, about the physical size of a school bus. This is a detector that operated in the US over the last decade or so. It's called microBoon. And what you see, actually, is a still from a roughly 2 millisecond exposure of ionization trails left over in the detector from various charged particles that went through the detector. Most of these lines that you see is actually cosmic rays raining through the atmosphere and onto the Earth and through our detector. And within these interactions, there are also potentially neutrino interactions from our beam or from elsewhere that could be hiding therein. And what we can do is we can dig in with our analysis tools, look for those interactions, and when we find them, we can further examine what they look like. And here is a zoom in 2D projected view of what it looks like when an electron neutrino interacts. So you don't see the neutrino, but presumably a neutrino comes in here from the left, and in its collision with an atom in our detector, it produces a proton, which doesn't travel very far, but it ionizes a lot, as well as an electron, which is much lighter than the proton. So it ionizes, but not as much. And furthermore, since it's light, it gets knocked around a bit and produces what looks kind of like a shower spray of ionization in the detector. To contrast this with a signature from a potential mu neutrino interaction, in this case, so this is to scale, it's about 10 centimeters, 50 centimeters. In this case, a muon is produced, which is kind of like an electron, but more massive. So it has a lot more momentum and can travel further and more of in a straight line, leaving behind a long path of ionization. It's barely bent. So we look for these distinct signatures, and this is how we can infer that both were neutrino interactions showed up in our detector out of nowhere, and secondly, we can further classify those interactions according to the neutrino type that we think was each one. Over the past decades, there have been dozens of experiments that have been carried out, studying neutrinos from the atmosphere, neutrinos from the sun, neutrinos from reactors, even neutrinos from accelerators. And what we do in these experiments is we have some kind of source of neutrinos. It could be our beam. We place our detector some distance away, and we're able to count, after the neutrinos travel a relatively short journey, the number of, let's say, muon neutrino beam, number of muons that are produced in our detector. And through doing so, we can learn more about how neutrinos interact and their properties. So we've been doing this, and what we've actually learned, to our surprise, over decades of experimentation, is that neutrinos undergo some kind of identity crisis. So what we know is that after a short journey, what we see is just muons produced by muon neutrinos in the beam. But after a long enough journey, or if we were to place detectors significantly further away, what we see is that sometimes muon neutrinos will produce electrons in our detector. This phenomenon is a quantum mechanical phenomenon that takes place over large distances, kilometers to hundreds of kilometers, and it's called neutrino oscillation. It's a very unique phenomenon in the particle world, and it's been revolutionary in our field. The discovery of neutrino oscillation at around year 2000 changed decades-old theories of neutrinos and really revolutionized this idea that neutrinos have non-zero mass. Okay. So there are two key experiments that were able to demonstrate this. One of them was a massive detector that ran in Japan, Super Kamiokande, studying neutrinos from the atmosphere, produced in the Earth's atmosphere and in cosmic ray air showers. What this experiment saw was that there was an asymmetry in neutrinos coming from above the detector versus ones that were coming from below the detector, the ones that were traveling a further distance through the Earth before reaching the detector. A similar signature was observed with neutrinos from the sun. And in 2014, the two experiments shared Nobel Prize for the discovery of this phenomenon, neutrino oscillation, which implies that neutrinos have non-zero mass. Understand this, it helps to think about time dilation. If something is massless, it's traveling with the speed of light. And if you're traveling with the speed of light, time is so dilated that, in fact, time stands still. If time stands still, you can't possibly experience any change. So, in order for neutrinos to experience this change in their identity, they need to experience time. They cannot be traveling with the speed of light. They have to be traveling with the speed next to the speed of light, and therefore they must have non-zero mass. Okay. The mass is tiny, which is very weird. We don't exactly know how much mass neutrinos have, but we have cosmological observations as well as astronomical observations and even observations in experiments that we can do in our lab and say that their mass is very small and likely around a millionth of the mass of the electron, or even less. They are tiny, and this begs a question, which is why so small? If we assume that all fundamental matter particles gain their masses through the same mechanism, the same underlying physics, it's most natural for us to expect that they all will have comparable masses. Their masses will lie closely to each other on a scale here shown in the vertical. At least that they would be evenly spaced. This is the case for quarks and the electron, muon, and tau. But neutrinos lie way at the bottom of the scale, and this is very bizarre, very unsettling. To give you a sense of scale, if the electron, muon, and tau neutrino were equivalent to a fruit fly, a mosquito, and a fly, then the top quark, another fundamental particle, would be the size of the Titanic. So to call this large, varied spectrum of masses as fundamental is very, to say, upsetting to physicists. So why is neutrino mass so small? That's a big question. And it actually makes us think that maybe the mechanism that's responsible for giving neutrinos their mass is not the same as the mechanism that gives mass to all other particles. In fact, we think that this small mass could be the product of something we call the Seesaw mechanism. So this mechanism predicts that the neutrinos that we observe and live with here today are these light ones over here on the right, are one of two kinds, and that there's in fact another kind of neutrinos, which is much, much heavier. And these neutrinos we've never seen, and they no longer exist in our universe. We can produce them. The seesaw itself is a ratio, which tells us that the heavier the mass of the heavy neutrino, the lighter the mass of the light neutrino. These heavy ones are about a quadrillion times the mass of the proton, such that we can't possibly dream of producing one in our accelerators. For example, the Large Hadron Collider, the highest energy accelerator that was designed to produce the Higgs, designed to produce something that's 100 times the mass of the proton. We're talking about something that could be a quadrillion times the mass of the proton. But these heavy neutrinos would have nevertheless existed early during our cosmological age of our universe, when everything was hot and dense and with enough energy for them to be produced. And there's another special thing about these heavy neutrinos, which is predicted by the Seesaw model, and it actually gives us for free a mechanism for generating the matter-antimatter asymmetry in the early universe. Specifically, the Seesaw predicts that these neutrinos are their own antiparticles. This is a property which none of the other particles, normal matter particles we know possess. It makes them special. It actually allows them to exhibit some type of symmetry violation in their decays, and such that when they decayed a long time ago in the early times in the evolution of our universe, what happened is that they left behind more matter than antimatter, and this more matter that they produced is basically what gave rise to our observable universe today. Okay, so we think that if this scenario holds, we think that this symmetry violation in the heavy neutrinos may be correlated with traces of symmetry violation with the light neutrinos. So a question we can ask is whether light neutrinos show any signs of symmetry violation, and in particular, they behave differently and do they oscillate differently? And this big question is what the Deep Underground Neutrino experiment aims to address. This is a major international project which is based in the United States. And I have a little video which shows how it works. So we're able to produce high-intensity proton beams in the US's premier particle accelerator in Illinois. These proton beams, we can accelerate them to high enough energy and with high enough intensity for directing them onto a target which produces other particles unstable, which decay to produce neutrinos. And we aim this beam underground, about 800 miles away, all the way to South Dakota, where something like a mile underground, we're going to build massive detectors. In these detectors, we're going to count how many neutrinos interact, and specifically how many electron neutrinos interact when we run with a neutrino beam, and how many electron antineutrinos interact when we run with an antineutrino beam. So we're going to run this experiment for about a decade, and in order to do that, we have to come together, a collaboration of something like 1,500 scientists worldwide with complementary expertise, and put together something that has never been engineered before. Yep. We're building the world's most intense neutrino beam, powered by a multi-megawatt blower at Fermi National Lab in Illinois. We're going to shoot this beam underground. Thankfully, neutrinos barely interact. That means we don't have to dig an 800-mile-long tunnel. And for our far detectors, we're going to use something like 70 kilotons of cryogenic liquid argon, which we're going to extract from the atmosphere, liquefied, purified, and fill these giant caverns deep underground. Just to give you a sense of scale, one of these, there will be 4 total caverns. It's about the size of the Pratt building in Denver. So we aim to begin construction of these detectors and beam by the end of this decade, and then we'll run and carry out this important measurement, comparing electrons produced in neutrino beam to positrons produced in the antineutrino beam, looking for signs of symmetry violation. Which is not the only thing that Dune can do. Okay. Once you build such massive detector deep underground, you have for free a beautiful astrophysical neutrino observatory. And we can look for neutrinos from supernova explosions. Supernova explosions produce a large amount of neutrinos. More than 99% of the energy released by a supernova comes in the form of neutrinos. And those neutrinos can reach the Earth and light up our detector over the course of about 10 seconds with about 1,000 such neutrino interactions. So by recording those interactions, we can witness in real time the dynamics of a supernova explosion. We might even be so lucky so as to witness in real time the birth of a black. Okay? It's not an easy task. Supernova neutrinos are actually about 1,000 times less energetic than the beam neutrinos, which means that they leave behind very, very faint signatures in our detector. Okay? And just to give you a sense, what that means is that we have to continually watch the data coming out of our detector. You can think of it as setting up in parallel something like 1,000 CRT TVs and watching static noise in the TV. Try and find within one of them, possibly, or a dozen of them, traces of what might be supernova neutrino interaction. These CRT TVs will be updating at a rate of 1 per couple of milliseconds. Okay, so we're talking about terabytes of data per second, and running this detector for 10 years. It's a huge challenge. Actually, in one such image, I haven't told you that there is actually a supernova neutrino interaction in there. You spot it. It's a little hard to see. It's that red dot right around there on the right-hand side of the image. Thankfully, we've been developing electronics for decades to be able to handle such data challenge. A detector the size of a school bus using last decade's technology would need about 200 such boards with powerful FPGAs on it, process all that data in real time and look for these neutrinos. Thankfully, over the past decade, technology has advanced. Now we have devices that are 1,000 times more capable in processing data. And so we can do that. And we can do that also with the use of real-time AI. And why go through all this trouble? Well, neutrinos are very special. Over decades of neutrino experimentation, they surprised us over and over again. Pauli, the physicist that postulated neutrinos to begin with, was very distraught when he had to come up with the concept of neutrinos. He called it a desperate remedy to propose a neutrino that he thought could never possibly be detected. But here we are today, studying neutrinos, finding them as extremely valuable for scientific research. Being neutral and weakly interacting means that they make excellent astrophysical messengers. We also can use them in real-life applications, for example, for nuclear safety, nuclear non-proliferation. You can monitor neutrinos from reactors at a distance. You can tell based on the rate of neutrinos that you measure and their energy spectrum whether the reactor is on or off, whether it's enriching uranium, for example. And overall, they're very special. Unlike other particles, they don't get their mass through the same mechanism that other ordinary matter does. And we think that that may be the key to some of the biggest mystery in our universe, specifically the prevalence of matter over antimatter. And I see I'm pretty much out of time. I want to leave time for questions. I won't tell you about dark matter, but go after dark matter in very similar ways as we do for neutrinos. And the two approaches are very synergistic. They but I'll leave you with this, okay? Chasing ghostly particles is not easy. It is exciting and it's rewarding to do so. And do so, I very much hope that we might just uncover the answers to some of the biggest mysteries about our universe. Thank you. And I can take your questions.
I got a question. Just two quick questions. Has an antimatter atom ever been observed or created, or just subatomic antiparticles?
Yes, we have been able to create, or I should say, yes, the question is whether an antimatter atom has ever been created. The answer is yes. Physicists have been able to produce antimatter atoms. They're very unstable. They decay very, very quickly.
Okay. And the other one is, you said that the detector material has to be really dense, obviously to increase collisions, right?
Yes.
I mean, could you give us an idea how dense? Like if the nucleus of an atom was the size of, say, an apple, how far away would the next nucleus be? Are we talking the top of Aspen Mountain or the next state over?
So the question is, we need these detectors to be dense in order to maximize interaction probability. The question is, what is the sense of scale between neighboring atoms? How dense is dense? I don't know the answer off the top of my head, but we're talking about densities of materials that we have readily accessible and abundant, and we can make big detectors out of. So, for example, argon is something we can extract cheaply from the atmosphere, and gas argon is not dense enough, but liquid argon is significantly denser. So that maximizes interaction probability.
When you're looking in the picture of the big neutrino for the Big Bang, the neutrino mill, yeah, I thought I heard you say that there's a necessary relationship on the size. Can you say that? And there's some why or how, or how do we know?
Yep. So the question is about the heavy neutrino and the light neutrino. And what is the relation between their sizes, and how do we know that it must be such? It's a great question. Not sure I can answer it in a very straightforward way without lots and lots and lots of math equations. The idea is that there is a certain scale that is responsible for normal matter, and that in a sense the product of the two masses will conspire to give rise to that scale, to be comparable rather to that scale.
Okay.
And so if you increase one of them, you have to decrease the other correspondingly, such that the product is the same. So that's equivalent to saying that there's a seesaw relationship.
Could something like Dune or other forms of neutrinos or dark matter turn into some sort of energy or power source that could be used in the future?
The question is, could something like Dune, maybe if I can paraphrase, can Dune harvest the energy of those neutrinos and turn it into some other form of energy?
Like power something.
Power something. In principle, you can harvest the energy of neutrinos and turn it into something else, use it to power something. That's a very inefficient way of doing so, because neutrinos barely do stuff when they go through our detector. So trying to catch them is like trying to catch butterflies through a net that is very sparse. So they just go straight through. There was another question. Yep.
You said that neutrinos tip the scale in the favor of matter versus antimatter. Do we know how, or do you know how, or what all this happened?
Yeah. So I don't know for sure. This is one theory that exists. People have thought of. So it is through such a model where you assume that the light neutrinos, which manifest in nature, have these heavy super partner counterparts. It's those heavy super partner counterparts that are responsible for they exhibit violation of symmetries that give rise to more matter than antimatter. We think that if this theory is true, this could have happened very early during our universe's history and basically just froze into the universe that we see today as excess matter.
Do radioactive materials like nuclear waste emit neutrinos?
Question is whether radioactive materials like nuclear waste emit neutrino, and the answer is absolutely yes. Any kind of nuclear reaction, most nuclear reactions, I should say, emit neutrinos or antineutrinos. So in these geoneutrino studies, for example, where people produce heat maps of neutrino abundance over the surface of the Earth, you can clearly see correlation with nuclear reactor sites, for example, across the Earth. And I imagine similarly with big nuclear waste sites.
There's one more question about that.
Yeah, to be said earlier, you didn't have time to go through a lot. I'm sure everybody would love to hear you go through it. That neutrinos could explain what dark matter is all about. I don't know if you meant dark energy also. I, for one, would love to hear anything more you can say about it.
I can say a few things about it. We know there's dark matter out there, and we know that it doesn't interact through the strong, the electromagnetic, or through the weak force. It interacts gravitationally. It might interact through some other force, which is even weaker than the weak force. So the most prevalent theories out there, or at least for the last couple of decades, is that dark matter is actually made up of neutral particles, similar to neutrinos, interacting even more weakly than neutrinos. There are other constraints that we have from cosmological measurements that also tell us a little bit about the abundance and mass of these dark matter particles. And it turns out that neutrinos may be a little too light to be a good candidate for dark matter. But it's not impossible. That's the case in the simplest cosmological model that you can cook up.
Okay, when you showed that slide of the different amounts of different why is it the stuffing? Why should everything be grouped?
Yeah. So why is it distressing that
Just
neutrinos are so far separated from the rest? It's a good question. In particle physics, symmetries play a big role. There's 3 generations of quarks, 3 generations of the electron, muon, and tau. Generally, we like things to be explained in a simple way, meaning if you can come up with a theory that describes one of these particles, that same theory should describe the others, more or less. So for that to come about, you need to have comparable properties. So that's just the hand-wavy argument for why this is so unsettling. But it is, to some extent, human predisposition to seek simplicity and symmetry in nature. We have time for one more question, or
Let's do. Like you had your piece. Yep, it's you and then will.
You said I don't know if I'll articulate this well. You said you study neutrino by the results of their interactions with other particles. But the neutrino seems so weak, it seems like the result of the interaction is fairly dramatic. How is that?
how can we say that neutrinos interact weakly, but the result of the interaction can be so dramatic? So the first part has to do with the probability of something happening. That's what we mean when we say neutrinos interact weakly. It means that when we smash X amount of neutrinos with X amount of atoms together, the probability that at least one pair will interact is very, very small. Whether the interaction will be traumatic or not actually depends on the amount of energy being put into the interaction. If you have highly energetic neutrinos, the interaction can be very traumatizing to a nucleus. Nucleus, in fact, can be broken completely apart by high energy neutrino. That's the distinction.
Next question. I read that there was, I'm not sure if this was theorized or actually observed, a fourth type of neutrinos. Can you speak about that a little bit?
So the question is, you read about a theorized fourth type of neutrino, and can I speak more about it? Thank you for that question. I actually spent, say, most of my career since my graduate studies looking for this fourth type of neutrino called the sterile neutrino. So the sterile neutrino is a hypothesized particle which is pretty light, like the other neutrinos, maybe a little heavier. But unlike the three neutrinos that we know, electron, muon, and tau neutrino, which we can produce and detect experimentally, that sterile neutrino does not undergo weak interactions. And in fact, people have considered it as a possible dark matter candidate as well. So we can look for such sterile neutrinos, depending on what exactly their mass is, through the imprints that they leave in neutrino oscillation. If they're there, they might interfere with how neutrinos change from one type to the other. And imprints are very small. You need very highly sensitive detectors to be able to do that very precisely. There is a big effort right now underway at this accelerator site in Illinois at Fermilab to try and resolve this question once and for all through a program called the Short Baseline Neutrino Program. So keep an eye out for new results over the next few years.
I think we're a little over time, so let's think. Should I just